at warm little ponds of the time that Darwin had in mind, because at that time, late heavy bombardment, land was not a pleasant place to be. Things were certainly more stable at the bottom of the ocean. And since their discovery in 1978, people have thought that maybe these black smoker type of hydrothermal vents might be important for the origin of life. Now, we think that a different kind of vent discovered by Deb Kelly and her co-workers in 2000, called lost city type of vents or off-ridge vents, might be more relevant for the origin of life because their chemical conditions are more conducive to life, not quite as hot and maybe a little bit richer in hydrogen. Now, the geochemical differences between these two types of systems are schematically illustrated here. On the right, you can see the black smoker kind of vent with the sitting directly above a magma chamber. Now, that magma is 1,200 degrees, and that's why the water coming out of black smokers is about 350 degrees. That's, we think, too hot for the origin of life. On the left, you can see the Lost City kind of vent, and there we think that the water coming out of the Lost City kind of vent is much cooler, around 70 to 90 degrees, and we think a very important process going on that's been characterized at Lost City called serpentinization is going to be important for the origin of life. That's schematically represented here. We've got water molecules being reduced by inexhaustible reserves of iron-2 in the Earth's crust to molecular hydrogen that leaves the vent in the effluent as these little white balls along with sulfur shown in yellow. Now, at the vent-ocean interface, the sulfur precipitates iron-2 and nickel, shown here in black and green, to give us transition metal sulfides. These mineral precipitates will have two very important functions, catalytic and compartmentalization. Their catalytic ability is going to be shown in the next blend in here. And transition metal sulfides have long been known to have very important catalytic abilities in organic chemistry. Here, hydrogen-dependent reduction of carbon dioxide to carbon monoxide, similar to what we see today in an enzyme called carbon monoxide dehydrogenase, maybe being connected up via methyl groups or methyl sulfide to acetyl thioesters, which we think are very important compounds. The most central compound in all metabolism is an acetyl thioester, acetyl-CoA, and we think that that has a reason. Now, the compartmentalization function is shown here. These little green dots are RNA precursors and amino acids here polymerizing into RNA-like molecules to give us the RNA world, and little peptides floating around there, but not genetically encoded ones. For that, you need the ribosome and the genetic code, and that we have right here. Every other theory for the origin of life has to solve this problem. We solve it here, but within these self-forming inorganic compartments, the contents of which then give rise to the common ancestors of the eubacteria and the archaea bacteria, which we think were acetogens and methanogens respectively. They make the transition to the free-living state, divide, and populate the Earth in its Darwinian evolution among prokaryotes since then.